In the previous example, we just looked at really a one-dimensional Runge-Kutta. We had a single state variable and we could keep updating it using that method of using our current state to get the next state if we also knew the derivative. But really, most of the time how we're going to use this is in multiple dimensions. We're almost always going to have at least two state variables, if not more, in the systems that we're looking at. And Runge-Kutta can handle multiple dimensions. And really, the method is going to look pretty much the same. The only difference here is we have vectors. So to get our next state as a vector, we're going to take our current state as a vector, plus the time derivative of our states, those x dot terms, and times the time step. So it looks almost identical to what we just saw. And this is the nice part about using the state space model. By taking our higher order systems, our second, fourth degree systems, and expressing them as a system of first order ODEs, we can use the Runge-Kutta method and the more extensive versions like ODE 4.5, because we can keep using this update method as long as we have first order systems. We can always use our current state to make an approximation about the next state. Let's look at an example where we have a second order ordinary differential equation. So we're going to have two state variables here. I'm not going to go through all the steps as before of going through it by hand, but at least let's go through some of the steps and compare what happens as the size of the time step changes. So that part will match what we did in the previous example. So here I have this second order differential equation. It's autonomous, it's not forced. So that's going to make this analysis a little bit easier, but even if we have forcing, the idea is still going to be the same. Our state variable x is going to be, well, I have an x double dot term, so x and x dot are my state variables. So that is going to be my x1, x2. And that means my x dot vector is x dot, x double dot. And that is going to then be x1 dot and x2 dot. So let's replace this original expression with our state variable expression. I have an x double dot that I have to express as x2 dot plus x dot, I'm going to call that x2, plus 2x, so 2x1 equals 0. Right, I have only one derivative term. I want to isolate that, so x2 dot equals, I have to move this to the right-hand side, negative 2x1 minus x2. All right, that is my first term, my first state derivative term. Now I need the mapping equation for x1 dot. x1 dot is the same as x dot is the same as x2. So these make up my basically collection of derivative terms that I'm going to use in my simple form of the Euler method or the Runge-Kutta method. So x1 dot is always x2, and x2 dot uses both x1 and x2 in order to solve it. So these are what I'm using to calculate my derivative at my current state. Now I'm not going to do this by hand and try to graph this one because it's going to be tough to graph this in two dimensions to keep it straight, but I'm going to graph them separately in Matlab of what's happening to x1 over time and what's happening to x2 over time. And actually, since x2 is the velocity, we're going to concentrate just on looking at what's happening to x1. So I'm going to take this state space model, the state space form, take it into Matlab, and again, look at different approximations where my step size is going to change. My update is going to change as I go. Same idea as the previous example. I'm first going to define now my two derivatives. dx1 is my x1 dot, and that was from the mapping equation. It was just x2. And my dx2, that's my x2 dot, that was negative 2 times x1 minus x2. So here I did explicitly put the 1 here. I didn't necessarily have to. And here I'm indexing my x vector, my state vector, that x of 1, this is my x sub 1 when I write it by hand. X of 2, or the second element in x, is my x sub 2 when I write it by hand. So here I'm going to start by looking at using 30 time steps up to 800 time steps and see what does that pattern look like as we go through. And then I'm going to compare that to the analytic solution, which again, the Runge-Kutta doesn't ever need to know the analytic solution, but we're going to be able to make a comparison. All right, so I go into, like before, the outer loop where I'm going to keep decreasing my step size or increasing the number of steps I take. And for this example, I'm going to go over from 0 seconds to 12 seconds. Again, this ST, that's the number of steps I'm using. So as the number of steps increases on each loop, my accuracy should increase. And as I did in the previous example, I'm going to pre-allocate my solution, my big X. This is going to have two columns though, because I have my X1 solution and my X2. So that's going to fill up my X. I will have as many rows as I have timestamps, and I have two columns because I have two state variables. Then I put in my initial conditions. We were given that the initial condition of X1 was 2, and the initial condition on X2, the velocity, was 0. Then I'm going to go into this update loop, and like the previous example, but now in a higher dimension, I'm going to compute my dx1, so what is my x1 dot? And that's what I use to update x1. So my new value of x1 is going to be the previous value of x1, that's what this is, plus the derivative at the previous point times the time step. Then I calculate x2 dot, and that's what I use to update x2. So my new value of x2, or my next value of x2, is my previous value of x2 plus x2 dot times that delta t. But do keep in mind that dx1 and dx2, or at least dx2, actually relies on both parts of my previous state, x1 and x2, to make that computation. So the dx terms can have both state variables in them, even though I'm updating one of them at a time. But it's the same basic premise. The new value of x2 is the old value of x2 plus x2 dot at that point in time times delta t. And then I'm going to plot the results here. And I didn't write it down, but I do have here the analytic solution to multiple decimals of this ordinary differential equation. So we can compare what we're getting numerically to the correct analytic solution, and that's going to again be the dashed line. Okay, so let's run through this just to get kind of the big picture of what's going on. So we see here, this is our figure. The dashed line again is the true solution, and as a general trend, we see that the blue is going to be using the fewest time steps between 0 seconds and 12 seconds. And then in general, as we get closer to the dashed line is when we are using more time steps. So let me zoom in just so we can see what's happening. All right, so again, blue is using the fewest time steps, then we have kind of this reddish orange, then this yellow, and then they start to really stack up. And as we get closer and closer and closer to the dashed line, we're using more and more time steps. Our estimates are getting better and better and better. I can keep kind of zooming in, and we see that eventually we get, again, to the hundredths place of error between what our approximation is finding and what the true value is. ODE 4.5 is going to get even closer than this because, again, it's using a better method than this very, very simplistic method that we are using. So the error is going to be most likely even less than to the hundredths of a decimal point. It's going to be better than that. But what we see is outside using, I would say the blue is using way too few of time steps. We're missing most of the picture. Once we use a decent amount of time steps, what's a decent amount? Well, it's going to depend on the problem. And that's the nice thing about using ODE 4.5 is it has logic built into it to kind of select a good time step for us that we don't have to necessarily know beforehand what time step we want to use. But to some degree, if we use enough time steps, we're getting a pretty good approximation to what the true solution is, and we're getting that without knowing the closed form solution. Again, we're only using the dashed line here for comparison, but all of the other lines were developed and found without knowing the closed form solution. They only used this very simple update method to approximate numerically what the solution for x of t should be. Oh, as a note, this is only plotting x1. I'm not looking at x2 here. So this is the solution for x1.